Well, life is a sequence of unexpected and improbable events, and one of them, for me now, the latest one, is this meeting. I'm so happy that the organisers were able to bring this off to see so many papers, people from the older days. How did we get started in density functional theory at all? John Harris and I had been working on a problem in surface physics, our original area. How does the interaction of an electron with a metal change as the velocity changes? But about that time, there was a minor controversy about the surface energy of a jellium. Calculations by Norton Lang and Walter Kohn in 1970 and 71 had used density functional theory, was not used as a term then. It was the inhomogeneous electron gas with local exchange and correlation energies. And in Hohenberg-Kohn paper of 64, which we all know, that this is that actual electronic systems do not belong to either of the two categories where the density functional theory can work. The Norton Lang and Walter Kohn had done a calculation on the, sorry, wrong one. That, I'm sorry, back I'll go. For a model system, a jellium half space, where you have a gas of electrons of a certain density, there is a neutralizing positive background with a sharp cutoff, and this was carried out for electron densities over a range typically from around the alkali metals around 5 to sort of aluminium, beryllium 2 or 2.5. They found if you made some changes in systems that are very high density, using a pseudopotential, you can get a very good description of the experimental numbers. Now, this was quite remarkable. We are looking here at systems with rapidly changing densities, and which are way outside any of the density distributions where this system should work at all, and we are getting good agreement with experiment. The controversy came because there were some calculations made in 72 by Craig and Schmidt and Lucas, who showed that the same agreement with experiment could be found by using extremely simple pictures where you looked only at the collective modes. When you introduce a surface, you introduce surface plasmons, you calculate the energies that are involved. This also gave rather good agreement with experiment. And as noted by Craig, this approach is really quite orthogonal to that of Lang and Kohn. Lang and Kohn were using the inhomogeneous electron gas under systems where this shouldn't work. How did we get involved? John Harris and I had been doing these calculations, and we decided to look and see whether we could answer that question. The surface energy of a bounded electron gas, we did this by a standard method used in many body physics, is to look at the interaction for the non-interacting system with lambda equals 0, the interacting system that we were all trying to model, and we chose an effective potential that made sure that the non-interacting density and the interacting density were identical. You can evaluate then the bulk and surface components of the energy, the exchange and the correlation energy via integrations over response functions of this system. This can't be done easily at all. For simple model calculations, we looked at the exchange and correlation energy for actually different for models, simple models, the infinite barrier model and the sharp cutoff model, which were both rather in vogue at the time. What astonished us when this came out, that the correlation energies for the surface energy contribution were about a factor of 6 higher than in Lang and Kohn. But also the exchange energies were about 50% lower than in Lang and Kohn's calculation, the local density approximation. But the sum of the exchange and correlation energy more or less tracked the Lang and Kohn results rather well. This is really quite astonishing. And I remember talking with John Perdue years ago. This was something that he and David Langreth had done calculations with a different usage of, different usages of the adiabatic correction scheme. And I've got this, let's get this one right. Oh. And he also came, this is it from their paper there, that once again, rather good agreement with the Lang and Kohn results, provided that you looked at not at the components, the exchange and correlation components. So he said, or they said, then the local density functional is good to better than 10% for the sum of exchange and correlation energies, but very poor for each one separately. Now, this is a real challenge. Why a local density approximation can make sense at all in a system which is very far in its density distribution from the systems for which it's obviously relevant. So this was a challenge for all of us and has stayed with us. How did this all work out for us? In 1975, John Harris and I shared a one-year position at Chalmers in Göteborg, and it was very important for the way this worked. As I said, in science as well as in life, you end up with a set of very improbable circumstances. Ola Gunnarsson was a graduate student in Chalmers at the time, and he was writing up his thesis, which was submitted at the end of the year. And we talked a lot. His thesis advisor, Bengt Lundqvist, was in Aarhus. And we talked a lot about density functional theory. But very important for the way we proceeded was that he told me about the new methods of electronic structure calculation that had been developed by Ola Krogh-Andersen in Lyngby. And I'd not heard of these. These were not published. They were not even submitted at the time. But I invited myself to visit Lyngby, and I was sort of impressed by the basis functions that he developed, these linearized muffin tin orbitals. And it seemed to me that it would be a good idea to try to use these methods in the context of molecules. So I firstly had to talk to my boss and convince him that it was worth putting 3 positions onto a project which almost everybody thought would fail. And he also should hire Ola Gunnarsson to come to Jülich to be part of that. That's how we started, and we started in September 75. 1976, Ola Gunnarsson and Bengt Lundqvist were published their basically the content of Ola's thesis. And at the end of that year, I visited Melbourne, and I visited a university there, and I gave a talk about local density calculations in molecules. And one of the audience stood up and walked around saying, "This can't possibly work. This is local density approximation, nonsense, you've got to do something else." And he managed to provoke me. I said, "In 10 years, you guys will all be doing these calculations." Now, I got the timescale wrong. 20 years later, I was back in Melbourne, and I gave a talk at a different university, and this gentleman came up to me afterwards and introduced himself, and I said, "We have met." And I reminded him of what had happened in 1976. He was, of course, doing density functional calculations, but he'd forgot the original data. These were our first results that we got, local density approximation using LMTO calculations. And we have here the results for H2. I'll put it down this way. H2, where they track very well the exact numerical answers. We see results for which you would expect then for the local density approximation, the overbinding of these simple molecules, and the binding distances were too long, and the vibration frequencies were too low. One thing that you can get out of the density distribution and knowing the charges is the change in the dipole moment, and we see here that the local density, local LDA approximation maps here rather well the change in the dipole moment as the distance between carbon and oxygen varies. I mentioned the work by Gunnarsson and Johansson, which was part of Ola's thesis, that they got almost exactly the same results as we got for H2, and they used a completely different basis. They used numerical algorithms, and we used LMTOs, but the results were basically the same. And of course, if you've got a decent basis, you should be able to get good agreement. Oh, I'm sorry, this one. Now, in 1977, we're tracking time here rather well, I was going to visit Cornell and wrote to Roald Hoffmann, and this was an indication, this was the first time that any chemist had said anything nice to us. I appreciated receiving the preprint of your work. The results you obtain are spectacular. Now, I had to take note of that because I didn't hear much like that from chemists for a very long time. I shall take you through a couple of molecules that we calculated at that time. I'm not going to go through details here. I'm going to look at 2 beryllium atoms. The beryllium-2 molecule, it's only got 4 valence electrons. You would expect you could describe this molecule very well, but Hartree-Fock gives no binding. And here is just a summary of some. I'll look at the names involved. You can see that there's the people you like, Ernie Davidson, Fritz Schaefer, and the rest, and also John Popel and Paul Schleyer. So the picture we have then, Hartree-Fock does not bind this molecule, and ones like it, and all the attempts to look at this molecule over the years had found either no binding or something very similar to helium-2, which is very weak, as a very weak minimum. So the results that, excuse me a second. So these results were really quite astonishing. Now, the molecules magnesium-2 and calcium-2 were known, and we can look at the results here, and you can see really sort of reasonable description of magnesium and calcium, excepting for the binding energy is overestimated by the local LDA approximation, which is something we had expected and which is something we got. Also shown are the results for the cohesive energy, this upper curve here. The X's are these are not our results, but from Mark Williams. And these results we have here that, once again, that there is a zigzag here, beryllium, and the cohesive energy, binding energy of the solid, and an overestimate resulting from the use of the local density approximation. I was really shocked to find that beryllium-2 came out much more strongly bound. Once again, it is certainly overbound because of the local density approximation, but it certainly exists and is, from these calculations, and is more strongly bound than magnesium-2. Now, I got an awful lot of ridicule from these results. 1 year later, there were some calculations from Liu and McLean at IBM in Almaden, and they found a much shorter distance. These previous calculations were all at very long bond lengths, and they found, once again, a much lower binding energy, but a result that it is certainly more strongly bound than magnesium-2. And Nick Handy was nice enough some years later to say that this was one of the first successes of DFT to the study of small molecules. A couple of stories. In 1978-9, John Harris spent a year at Oak Ridge, and he wrote me a letter. We had letters in those days. We didn't know no emails. He'd been to a conference, and he said he'd talked to a very smart guy who had proved density functional theory on a very small piece of paper. And that was Mel Levy, of course, and Mel was, of course, right then, and he's usually right about everything else. I want to say also I was at a meeting in 1980, and there was Bill Goddard III. And I said, I would like you to calculate beryllium-2. I said, either we have a system where density functional theory is producing rubbish, or there's something wrong with all the calculations in the literature. And I said, will you do this calculation? He said, no, there's nothing in it for me. Either you're right, which is okay for you, or you're wrong, which I expect, and therefore there's nothing, once again, that's nothing new either. Well, 20 years later, I visited his group in Pasadena, and I said, I gave this story to his group. And he sort of smiled and stood up and he said, of course, when he got back to Pasadena, this was the first thing he did. And I said, what did you get? He says, the same rubbish as everyone else. 1983, some of us were at a workshop in Santa Barbara, and I mentioned this. Mel Levy came up to us and he said, you know the reason why your project has been a success? And I said, tell me. He says, because you don't know any chemistry. He said, if you'd known any chemistry, you wouldn't have done this project because you knew it wouldn't work. But you didn't know that. So he was right on that one too. We moved on to larger molecules, and this turned out to be not so successful. In these molecules, the standards of water, ammonia, and CO2, we got a rather good description of most of the features, including the vibration frequencies of that reproduced experiment rather well. I thought really quite satisfactorily. But Hartree-Fock also does a good description, provides a good description of these molecules. This was I was then visiting, I was back in Sweden, and I visited Lund. And I mentioned these things to Björn Roos. And he said, you're doing the wrong molecules. these molecules are described well by Hartree-Fock. Why bother? I paraphrase. And I said, give me a molecule where Hartree-Fock is a disaster so I can find that. And that's what we did with calculations on ozone. Our computers then were not what we've got now, and it took me roughly almost a year to map out the energy surfaces on the ozone molecule and optimize the structures for C2V symmetry. Now, Hartree-Fock gives a disastrous picture here because we have the wrong ground state, this triplet here state, which is in fact some volts higher than the experimental ground state, is the ground state in Hartree-Fock by a large amount. And both of the structures, this one we're looking at and that one, are unstable with respect to 3 oxygen atoms. I was checking my literature, and there was a scattered wave X alpha calculation here by Dennis Salahov and Dick Messmer, and they, in that paper, I mean, maybe we can check this later, they also, with the X alpha scattered wave method, came in with the right ground state and with a reasonable picture of the relative energies. In 1985, I abandoned LMTO calculations. Dennis talked about the advantages of being able to do dynamics, and this is something that that really interests somebody who comes from the condensed matter world. And this, when he also mentioned the importance of Michele Parinello, and we adopted in 1985 the Parinello method, which we've used basically ever since. Now, I want to give one anecdote from to give maybe people here that are not convinced a feel for what was going on when we walked around and gave talks. The German-speaking theoretical chemists meet once a year, and Jan Behrens mentioned that I gave a talk there. But the interesting thing was this was the first time I really had contact with a large group of chemists. And I thought that I could make contact with them by quoting something from a well-known chemist. And I ended my talk by quoting Bob Parr. And this is a statement from an article he wrote in '83, and it's basically something we all accept now. This is a good thing to look at, this last one. Much research is needed to bring density functional theory to maturity, but there will result a substantially broadened and more useful quantum chemistry. Most of us would subscribe to that. The point is that after this talk, an extremely well-known theoretical chemist in Germany came up to me and said, "Don't quote Parr." And I said, "Why not?" And he said, "Weil wird nicht ernst genommen." He's not taken seriously. Now, this is 1985. I thought you'd like that. He's not taken seriously. Wow. Now oh yes, in 1990, I was at the Sanibel meeting, and that was the most interesting. But I put this up here simply because of a comment here about Ernie Davidson. Normally a quite level-headed individual and a thoughtful theorist. Someone asked him at the end of his talk, I've forgotten which calculation he'd been doing, what would you have got with density functional theory? And he was so negative. He said, "Don't talk to me about that method." I mean, this is the sort of stuff we've been facing for 15 years at this stage. Here is a calculation that we're using the dynamics, the car parallel method, where you have temperature in there and where you can look all over the do dynamics and look all over the energy surface. And much to my surprise, for 40 years, the only structure of the phosphorus-8, this is really a simple system, right? It's going to be a cube. It was the only structure that had been considered by anybody. One night on our grey computer at the time, it came out looking quite different. This structure is 40 kilocalories more stable than the only structure that had been looked at in the chemical literature to that point. Krishnan Raghavachari was the referee of this paper, he told me. And he said that when he got it, he saw the new structure, this different structure, lower symmetry, and he went like that. And before reading the rest of the paper, he went and did an MP2 calculation. And he also got a structure which was about 40 kilocalories more stable than the only structure he'd considered to that point. I mentioned this. We're doing local density calculations. We're going to get wrong answers for the total energies. But we are, because of the particular methods we're using, we can identify maybe a structure like beryllium-2, which had never been found, and phosphorus-8, which was also unexpected at that time. Wei Tao has talked about the Monton meeting, and it certainly was also in my eyes a sort of a change, a paradigm change in theoretical chemistry. He also mentioned at the beginning there was a talk by John Popel, which was certainly very negative about density functional theory. We had also Axel Becker's results, and this caused people to have pause for thought. I gave a talk there. Wei Tao showed the abstract, and I happened to bump into Popel after the talk, and I said, "Why don't you like density functional methods?" And he said, "Because your energies are not good enough." I mean, who's going to argue with that? But I said, you don't measure total energies, you measure energy differences. Well, he didn't comment on that. But at the end of the meeting, he gave a talk summarizing what went on. And I was there and sitting, and I was really feeling very uneasy. A very smooth, polished speaker, and saying nice things about density functional theory, but I was uncertain about how he really felt. So that was very interesting. But of course, as we all know, he went back to his home base and then did some calculations on it. I will mention here one meeting there in 1992. And I met David Wales in Chicago. This was a meeting where actually it was the first time I'd met Dennis Sullivan. And he said to me, "Oh, we've gone density functional theory. Nick Handy is completely convinced." And this was a surprise to me because he'd been a big critic of ours. And he said, he's getting interesting things every time. He came in yesterday and he looked at the change of the dipole moment in CO as you change the separation. I said, we published that 15 years ago. And, well, that was it. But I said, why did he change? Why has he become a density functional man? Because Popel did. And of course, at the end of 92, this first paper from Peter Gill, will maybe talk about that later, and that the initial results of using the Beckett exchange functional were very good and very encouraging. One thing that Peter doesn't know about this paper is that I was the referee. I promise you I wasn't going to bounce that one. We can leave that one out. I want to say something about density functional calculations in condensed matter physics, which is where I come from, and where I guess I'll stay. That here is a calculation which is an enormous number of density functional calculations. If you are looking at a simulation of liquid bismuth using a density functional approach, and you want to get decent statistics and to understand the nature of the collective excitations in this material, then you have to work very hard. There are transverse and longitudinal modes. One method of looking at the transverse modes is to calculate the viscosity, very difficult thing to do. And really quite remarkably, we can map the experimental numbers here over a large temperature range. The experimentalist who is basically responsible for this calculation, the agreement of your results with inelastic X-ray scattering is really quite beautiful. And he thought that the differences were more likely to be from the experimental side than from the calculation. You don't often convince experimentalists like that. This is a topic that has been my main effort for the last 15 years, is the crystallization in a material which is the basis of most of the phase change materials used in storage, like in the DVD or Blu-ray disc. Now, this is a calculation that involves large number of atoms, a small time skip, and this means that these calculations of looking from how this, wrong one, this amorphous material turns into a crystalline material, there you have to be very patient. You need a lot of computer time. There are, in this calculation, more than 2 million self-consistent density functional calculations for hundreds of atoms. To watch the crystallization take place, I can't show it here, but I've got it on my computer, I can show anyone who's interested, is a remarkable thing. It gave me the feeling that I almost could see exactly what was happening. And in fact, you can learn much more from this than you can from most experiments. The differences, our problems here with how are we going to talk about the differences between condensed matter physicists? Here we have the typical versions from Walter Cohn, that he had an enormous amount of problems. He said that the theoretical chemists were highly critical, not to say dismissive, of DSV. After a particularly nasty bout with a referee, I asked John Light, then editor of Journal of Chemical Physics, what do you think about density functional theory? And he said the local density approximation and the use of our particular basis sets. Fritz Schaefer also said similar things, and I will summarize them in the next slide. What are the criticisms? Some of them are accepted by everybody. the main things are the electron, I would say the electron gas methods, the inhomogeneous electron gas, much more familiar to condensed matter physicists than chemists, and the poor total energies, which I don't know are correct. And we have here John Popel saying, at the present time, the principal limitation of DFT is there's no clear route to getting the exact energy. Well, you can see from the examples I've showed, the condensed matter world, that it did not enter my head that we needed to get the exact energy for all of these millions of simulations, but you must have a very good description of the energy differences. The electron gas models go back to 1900 and the work of Drude. They are very familiar to the chemists. We learn about them to 1900. It's after the electron, but before we knew that there was a point nucleus. And these can be fixed up. I mean, there are some dramatic problems. The quantum mechanics solved some of them because you have fermions and not Maxwell-Boltzmann statistics. And of course, one has to mention something we know about, the Thomas Fermi.
Okay, I think time is running out here.
Okay. I will just say that we, from the condensed matter world, it's part of our meat and drink. The first 3 chapters of Ashcroft and Merman are on the Drude model, and there's much more in it about it. This is something which is very unfamiliar to most chemists. And here is Nick Handy. We do not think that many chemical problems need an exact treatment of the electron gas. And of course, this quote from that he says that we haven't been able to make jellium. This is right, and this is the shows that we have quite different perspectives on the total energy and on the electron gas. And I will just finish by saying that when I say 50 years in density functional theory, this is not quite right. I mean, the people I know here, I've been doing for the last 20 years more applications of density functional calculations rather than density functional theory. And so I don't see most of the people here when I go to meetings. I see other people's, and it turns out that you can have fights with them as well.
Okay. I think lunch is waiting. We can take one comment, and then, yep, quick one.
Could you agree to the idea that the Hartree-Fock theory, beautiful as it is, it's like the central point of the whole argument. And there are 2 ways to correct for the errors of Hartree-Fock. One is to go into CI and the direction preferred by most quantum chemists. The other way is to realize that there is a rather obvious error in the form of the delocalized hole of an electron in Hartree-Fock. That means that when you stretch a system, it has an erroneous dissociation problem. And you can actually correct that by simplifying the exchange part of Hartree-Fock. And so therefore, you know, one needs to realize that approximations of DFT type that localizes the exchange part will actually cure the dissociation error and will help in many ways to give better results. But of course, if you are a quantum chemist, you want to do it the other way, namely to push in some CI and proper correlation, cure it that way. It looks harder, and you know, if you take your BE2 problem, you know, they had to struggle a bit to
Oh, yeah.
to get the error corrected. But you know, by localizing the exchange part, you could get a good answer quite readily in a fairly simple-minded.
Right, I agree with all you say. I forgot to, I had to skip over the Hartree-Fock. If you apply the Hartree-Fock to the homogeneous electron gas, you find a zero density of states at the Fermi energy. And this is something that condensed matter physicists, for a description of a metal, don't find very attractive.
Okay, you seem to have something very important on.
Just a 30-second comment about BE2, which is while I'm not an unabashed defender of the Hartree-Fock method, it gets BE2 quite nicely, provided you spin polarize the orbitals. In other words, it's very much what you have to do to break a bond in Hartree-Fock. You've got to spin polarize. It actually gets the short bond length.
Okay, thank you. So on that comment, I think